Please welcome to the stage Silvan Aeschlimann, Rory Jacobson, Anu Khan, Dr. David Luebke, and Dr. Mijndert van der Spek.
Good morning, everyone. My name is Silvan Aeschlimann, and I'm a manager at RMI CDR Initiative, where I lead our efforts on direct air capture R&D. As you've just heard from Daniel, we've done a lot of work over the last 2 years roadmapping direct air capture, and have recently published our DAC RD&D roadmap to 250. But obviously, it's never possible to cover everything, and it's a very fast evolving field. So I'm excited to be joined here by all these panelists and discuss what they see as the most important R&D and D priorities. Let me introduce your panelists. Rory Jacobson, Senior Advisor for Deployment at the US Department of Energy. Anu Khan, Deputy Director of Science and Innovation at Carbon 180. Mijndert van der Spek, Associate Professor at Heriot-Watt University, and Dave Luebke, Technical Director at National Energy Technology Laboratory. A quick announcement before we get right into the topic. Yesterday, we received quite a lot of feedback that audience questions would be highly appreciated. So you asked for it, you're gonna get it, but please be prepared afterwards. Let's dive into the topic. We all know direct air capture is largely a numbers game, and figuring out which technology can achieve the lowest cost and lowest energy requirements by 2050 is literally the $1 billion question. So given we have a room full of representatives of different startups that all believe in their technology, I thought a spicy way to kick off this panel would just be asking you all what you consider the most promising approaches to direct air capture. Mijndert, I'll start with you. Could you give us a brief overview of the work you do at Heriot-Watt University and what approaches to DAC you consider the most promising at scale?
Thanks, Silvan, for giving me the opportunity to be here with you today. So my work is actually very much focused on technology assessment. At the same time, we investigate materials for direct air capture at Heriot-Watt University. And we really try to make the combination between materials and processes and how certain materials may perform in different direct air capture processes. So we characterize the materials, we model them, we do TEAs, we do LCAs and upscaling, etc. Now, on your question, I think this is a question that many people always ask, and to my mind, we really need a portfolio because the challenge is so big, and I think that many different technologies may perform better or worse in different environments. That we shouldn't really bet at one technology at this point. So to my mind, really a portfolio approach is very much needed.
Dave, I'd like to dive a little bit deeper into the idea of a portfolio. I think we can all agree that there won't be any silver bullet DAC technology, but one thing that we're seeing in the industry is that kind of like the first generation direct air capture technologies, they have been focused on producing simple systems with components and materials that are already available. Now we basically see more startup emerging that focus on electrochemical approaches, with the target of not so much reducing capex in the very short run, but reducing opex and energy requirements. Given your perspective working at the National Energy Technology Laboratory, do you think that could be the future of DAC?
So let me give you my perspective working at the NETL for a long time. I'll give you the old man's perspective here. So when I got into point source capture, R&D in 2002, that technology was very much where we are today with DAC. Over time, what we saw was the original generation of technologies that were out there as we first started to do this work really matured and grew, and future generations, second gen, third gen technologies came into being and were developed and scaled up, and we learned a lot. And by virtue of doing that work after the first few generations of technologies had gone by, those technologies addressed some of the shortcomings, and it's left us with, in point source, a quiver of very strong implementation-ready technologies there. I suggest to you that that's what we're going to see in DAC as well. In the early 2000s, we spent a lot of time thinking about, hey, which of these are the best technologies? How quickly can we down select? How quickly can we pick the best so we can focus resources there and really get these things to market quickly? I'll say, as a community, we weren't extremely successful at picking winners then. I think if we try to pick winners today, we won't be extremely successful in doing that either. So I very much agree. Let's develop these technologies. Let's push them forward, as many of them as possible, as fast as we can. And let's let the natural forces of the market and the R&D effort do the down select for us, so that when we are 10 years from now, and I think we have, those kinds of timelines to get these things pushed forward, we'll have more options, and when we understand the issues that will come up as we do this R&D, we'll have more ways of addressing them.
Thank you. Rory, you're both involved in the DOE's work around DAC hubs and mission innovation. Given that most people or some people in the room might not be aware of what exactly mission innovation does, could you give us a brief overview of what you do and how that has shaped your perspective on what DAC approaches are the most promising?
Yeah, absolutely. And thank you to our host for letting me speak on behalf of Fossil Energy and Carbon Management this morning. Mission innovation is really a convening platform for governments to have a conversation about their contributions to innovation on an entire suite of clean energy technologies. And currently, carbon dioxide removal is one of those pieces, which includes direct air capture. We are co-leads as the United States government with Saudi Arabia and Canada on this particular initiative. And there are a couple aspects that I think are really exciting about the Mission Innovation CDR Launchpad. The first thing is that we're also doing roadmaps, but they're roadmaps that are agreed upon by multiple national governments. So we're making key decisions about the geophysical opportunities that various national governments have within their priorities and their capacities. The other piece I think that's really, really exciting is a commitment to deploy at least 1,000 tons by 2025. And that might seem like a small number, but we want to ensure that everyone has a capacity to participate in this particular launch pad. There's also a collective contribution of, at minimum, $100 million by 2025. With US's current policy alone, we've already achieved that. And so I think it's a phenomenal opportunity to, one, be transparent about, I think, what Dave is talking about with respect to some of the life cycle and techno-economic considerations of these various technologies, but also to share how we're learning from the policy that we're deploying in our own domestic governments and the takeaways that we have from our own market dynamics. So it's really a convening platform to understand both the policy priorities of different nations with respect to CDR, but also what we're learning about the technologies.
Thank you. Anu, you have a very, very unique perspective because you both study electrochemistry and you're now focused on MRV. One of the aspects that is critical for direct air capture, but is sometimes kind of neglected in the public discussion. How has that shaped your perspective on what you consider most promising within the wide portfolio of DAC technologies?
Yeah, first and foremost, thanks for inviting me to join this panel. I think, why do we want a portfolio is a really good question. I think there's this talking point that we have, we need a portfolio of solutions, both across CDR and also across DAC technologies. And I think from the policy perspective, the reason that we need a portfolio is that deployment of CDR needs to be context specific. So there isn't, a DAC or CDR that exists in isolation from our broader climate policy and our broader climate goals. And we need the right solution in the right context in the right place with the consent of the people who are parts of those projects. And a portfolio of solutions helps us get there. So we don't want to lock in a specific technology, a specific approach, a specific form factor, when what we will need is a suite of climate solutions, including a suite of carbon removal solutions. And that takes us into the point about MRV, where, again, the standards that we need for carbon removal must be fit for purpose. It depends what you are using the carbon removal for. And often, I think what is missed in MRV is that there's a lot of technical questions. There are also a lot of policy questions baked into these standards, checklists, whatever you're doing. But sticking to the R&D piece a little bit, for direct air capture, I think there's a general sense that in some ways it is simpler. We know how to put flow meters on things. We know how to monitor CO2 and calibrate those flow meters, and there are rules for those. But it's not fully solved yet, and I think we need to be honest about that. So, for example, I think storage is a really big open question. I mean, there's a lot of things we know about storage, but most of the CO2 injection in the world, I think like 80% of it by volume, has been EOR. And so, or enhanced oil recovery, I was supposed to know that, but I think we're going to be injecting in different sort of geologic formations, different volumes, different considerations. So there's still a lot of learning there related to MRV. And then I think the other piece that comes to mind for R&D as it relates to MRV is I often ask verifiers, like, where do you think the fraud will be in DAC? Like, where is it gonna, like, where are the wheels gonna fall off? And the answer is often it's MRV. Fundamentally what it does is you kind of check if your operational data matches your claimed outputs. Does everything that happened in your facility match the amount of CO2 that you're claiming as credits? And we need more data about what we should expect about the operation of the facility in order to do that well. We need to know about the energy use of these materials in order to map it to outputs. And I think you're going to speak to some work you're doing because we need to build that data set essentially to do MRV well.
I saw a lot of nodding across the entire group. Does any one of you want to follow up quickly?
I just find it funny, for instance, that that Anu said we know how to do transportation and monitoring of CO2 flows, and the fact is that these standards aren't actually completely there maybe yet. So one of my colleagues, Professor Maroto Valer, is actually doing projects to make sure that the current flow meters actually do measure CO2 flows in the different thermodynamic regions accurately enough to be used for financial metering, if you will. But so the good news is yes, they do, but we didn't know that yet.
Dave?
I think that speaks to a broader issue, which is that it's early days. If you look back 5 years, you see just peer-reviewed publications. They've gone up by an order of magnitude in this area. So in some ways, we don't even yet know what it is we don't know. So we're working through those things, and we're doing it quickly, but we're very much in a position where we're going to get some surprises over the next few years, and we're just going to have to deal with those.
And I think that speaks to a broader need for data transparency as we're doing this work, because the field is going to evolve, but if it's happening, sort of behind closed doors in a space where the researchers don't have access to the information, we're not able to collectively update our understanding as a community, that's going to be really hard.
Do you mind if I continue?
Yeah, go ahead.
I think that is really interesting, and I think the way the DAC community has evolved is a little bit. It goes against how things go traditionally. So, one of the very first companies was Climeworks, and yes, the two founders they came from a PhD where they worked on the direct capture, and they found a company, but they didn't find that company based on a very, it was just one PhD, right? It was not like a very solid, agreed upon scientific body of knowledge. And this is what I like about direct capture, is that there's so much enthusiasm about it, that many people and many startups are just going ahead, but the scientific basis isn't there yet, or it resides within these companies. And it's very important to get to get many more measurements out. And many more studies out on materials, on process design, on process optimization, so that also the general public can form their opinion, including governments, including NGOs, including investors. Because otherwise, we just have to rely on what the companies tell us, and that will by definition be slightly more, slightly less biased.
There was one aspect in Anu's original response that I would like to follow up with you guys too, starting with Rory. Anu, you said DAC doesn't exist in isolation. We're going to need context-specific DAC. So one thing that we're seeing right now too is we don't only see electrochemical DAC companies emerging, but we basically also see DAC companies emerging that don't focus on pure play DAC anymore. It's not just about carbon credits, but they're materializing side products. For example, hydrogen. A few examples are Capture 6, Green Light. Do you think that's something that's going to continue, or are we going to go back to pure play DAC again?
I think it's yes and. As DOE, I think that we support both reactive capture approaches and, of course, pure sequestration. We have a utilization program that's existed longer than our carbon dioxide removal program. So I think it's important to understand that there are a variety of different use cases. I do think that, considering fit for purpose DAC, it's important to understand that DAC is going to have a ton of different iterations in different contexts based on the locally available energy resources, the perspectives of community members, and then, of course, the applicable end uses, whether or not there's readily available clean energy that you can use to convert the CO2 to valuable products, or if there's readily available geologic sequestration. So I think it's context dependent ultimately, and I think that over the next half decade or so, we're going to have a really, really firm understanding of how our policy mechanisms help to shape the types of DAC that emerge.
I've just heard a lot of kind of like votes on things that are needed. I would like to move on to another topic area, kind of like prioritization, collaboration. So how do we make these things happen? And just one first thing I'd be interested in, where do you see low-hanging fruits with respect to DAC, RD&D, and specifically where can just little dollar make the biggest impact, starting with Dave?
So I see a lot of potential in process optimization. So there are a lot of interesting materials that have been proposed out there. Let me back up a minute and say that when I got into this a couple of years ago, I did back into this. I didn't immediately think, okay, we're going to see a bunch of materials make real progress and major changes in sort of the overall basic technology that underlies DAC. I figured we'd move forward with what we had for a while, but there's been such a blossoming of work in the area that we are starting to see major changes in materials. Now, what do we do with those? How do we adequately create processes which are optimized not only to deal with the normal things that you deal with in a chemical process, like how do you best use your heat? How do you make use of integration to get more energy out of the energy that you have? But also, how do you do that in varying climates? How do you do that in specialized situations? I think we have excellent tools for looking at some of those sorts of things. I think the amount of R&D dollars that need to go into it to make the impact is relatively small. And so I think that over the next few years, I think we'll see some very interesting advances in the area.
Thanks. You just gave a vote for process optimization. Mijndert, I wonder, would you second that?
I mean, if you're talking about what are the more affordable things that we can do, then the kind of desk-based studies that David mentioned are certainly perhaps a lot of value for your dollar or for your pound. But the problem is a little bit that we need to do everything before 2030. And that's kind of what we saw in our road mapping work as well. And the previous speaker, Daniel Pike, already highlighted that, right? So we need equipment design, dedicated, but also generic. We need materials design further. We need process design optimization. We need many more TEAs for many more different situations, plus LCAs. We need to investigate how to integrate direct air capture into larger energy systems and their industrial systems at scale. So not just one plant that can take a little bit of waste heat from here or from there. And contrary to what other people say, I do see a serious challenge in powering all these DAC. I mean, the sheer amount of DAC that we need, because everybody's claiming the carbon neutral electrons, right? CO2 utilization says we can do it electrochemically. We're electrifying transport, we're electrifying homes. That's all nice and well, but if we want something to be left for DAC, we need to scale up clean energy much more as well. So I think we need all these things, all these R&D things by 2030. So I wouldn't focus on low-hanging fruit. We need a lot of investment into R&D in the next 7 years, because if we don't do it now, then we won't have DAC at the price where we want it by 2050 when we really need it. So I wouldn't think in terms of low-hanging fruits in that sense.
Now, two things I've heard yesterday and also earlier this morning when I was following Daniel's speech from behind the stages, we have a lot of calls for collaboration, but at the same time, I also hear a lot of people in the audience when I talk to them saying we're in an echo chamber, right? So we're basically saying we should collaborate. Everybody agrees we should collaborate, but the main question is not should we collaborate, but how are we going to collaborate to basically make progress in this industry? Now, Anu, taking a practical example, how would a multi-stakeholder collaboration involving academia, NGOs, possibly governments, look like for MRV?
I'm so glad you asked. As some of you know, this is my obsession. So I think what we see right now in MRV and standard setting for carbon removal broadly, certainly for direct air capture, is that it is primarily market-led, it's market-based actors, and that makes perfect sense across industries. Industry has the greatest incentive to create standards and have reliability and quality assurance across that industry. And carbon removal is fundamentally a public good. It will be largely publicly funded at scale, and the standards and MRV for carbon removal need to be designed with the public's interest in long-duration storage embedded in the processes. And so I think what we really need is that voice to be a part of the process and to be fully funded as a part of the process, both through civil society, NGOs, academics, having a full seat at the table when it comes to designing MRV and being able to ask some of these questions of how should we make this choice about LCA such that we are capturing the full set of implications of, as you were saying, scaling up energy use for DAC. What are these broader implications? And that's not to say this should happen in a closed room with just some academics and NGOs and maybe a government person sitting there. It should be a broad collaborative effort, but it should be one where we're really confident that the public's interest in long-duration carbon removal is fully represented in that process.
So Rory, I saw you nodding, so I'm going to come straight to you. And I'd like to expand the question for you a little bit, because both the DAC hubs and mission innovation, they're kind of like, by definition, large multi-stakeholder collaboration. So what are a few principles that we should follow for successful multi-stakeholder collaborations?
That's a great question. So I guess maybe starting, I wish that all of you could join our conversations through Mission Innovation, because they are phenomenally interesting and extremely collaborative, but they are government conversations functionally. But we are making decisions about what best practices look like, not necessarily explicitly for MRV, but certainly for life cycle analysis, certainly for techno-economic assessment. And I will shamelessly plug that we have been producing documents as Department of Energy on a number of best practices for life cycle assessment. So we've currently issued a direct air capture guidance on best practices for LCA. We're actively working on some other CDR pathways. But I think multi-stakeholder collaboration is really hard. And I think that DOE has actively tried to be a venue for that collaboration to the extent possible. But ultimately, I hope that Mission Innovation is a convening point for industry, NGOs, all of the stakeholders that you listed, and particularly also community members, folks that have a vested interest in the public good, to participate actively in what governance and public policy looks like for their country. Because I think it's going to look very different based on geography, as we've discussed.
I'd like us to move on to kind of like the area of questions that I consider from my perspective most promising, because I think it's even harder than the ones that we just talked about. When I follow the mainstream debate around that, kind of like outside the bubble, in my head, I always distinguish between three different types of groups. Basically, the one group that doesn't even know DAC exists. Then the second group that basically think DAC has potential and is going to be an important component of our climate mitigation portfolio. And the third group that basically thinks direct air capture is just a distraction from other more important climate solutions. So I would like to zoom in a little bit on the middle ground of these perspectives, apart from the group that just doesn't know about DAC, and basically ask, DAC hasn't been proven at scale yet. We don't know for sure whether we're going to get costs down, but I wonder, what are proof points that we need to reach by 2030 and 2040 to basically keep believing in the viability of this technology? Mijndert.
Would you mind if I just jump back and reply to Rory's comment? Because I think there's one, I absolutely agree with what he said. Is it okay, Silvan?
Sure, go ahead.
We've mentioned DEAs and LCAs a number of times, and I think they are critical in understanding what are the benefits or the merits of a technology, and also the disadvantages, because let's face it, there will be some. The problem is at this moment is that we don't have the input data for DEAs and LCAs. And it also, going back to what David said, yes, there have been dozens, if not hundreds, of materials developed, but none or very few of these materials have been characterized to such an extent that they can actually be modeled in a process model, right? So we cannot assess the performance of many of these materials in an actual process setting. And I think that is, from a scientific perspective, that's a massive gap that we need to tackle immediately, because otherwise you can have heaps of guidelines that are probably I know they will be very good, but then we still can't do the LCA and the TA.
Rory, I'll let you respond because you already raised your microphone.
Yeah, I would love to. So I think that is part of the really important spectrum of innovation commercialization that DOE covers. So we work on technologies all the way from functionally TRL 1 or 0, like basic material science and physics, all the way through commercial deployment and direct air capture hubs. And I think that TRL 1 through 9 journey is extremely challenging. I think a lot of materials will fail along the way. But I completely agree. There is a lack of input at the top of the funnel for basic materials. And I think that's part of what we're trying to solve with the carbon negative shot and many of our initiatives at DOE. So agreed, but I also think that we're actively working on this, and I know it has to happen by 2030. But there's a lot of work to do.
I now would like to get back to the original question I asked and get a little bit specific, because if I just put myself in the shoe of a non-DAC advocate or a critic, I'm coming myself from rural parts of Switzerland, so from places where people sometimes don't even believe climate change is real. So assuming you all convinced me climate change is real and we need DAC, but I'm still skeptic. And I basically say, all right, we're going to invest this technology, but what does this technology need to prove till 2030? And what does this technology need to prove till 2040? What are you going to respond to me, Anu?
I will respond that research for DAC should include social science research, both basic and applied social science research, and so that the communities that don't know about DAC or the communities that are unsure what it is, I think we need to do a lot in addition to the technical science and engineering or physical science and engineering research. We also need social science research. We need to understand what a just transition that includes CDR and CDR-like direct air capture means for our society broadly. And I want to be really clear that social science research is not the same thing as community engagement on a project basis. So I think a lot of times we kind of lump these things in together. If you're doing, even, good best practice community engagement, that is different from non-participant observer social scientist in that space. And so I think we really do need to think about dedicated, coordinated, social science research initiatives around something like the Regional Direct Air Capture Hubs program, where we're doing this for the first time. There's a ton that we can learn from it. And I am not myself a social science researcher, but I talk to folks in this field and they're like, I am part of a DAC hub project. It can't be me. There needs to be a separation between the folks who are doing, good community engagement for specific projects and folks who are doing research on these topics. So really, what do we need in terms of proof points? We need dedicated social science research. We can't just keep asking Holly Buck to do everything.
Although she's doing it very well.
It's so good, but...
If I was not playing devil's advocate, I would say I love social science research. I'm all for it, but I'm still not convinced. And I would be asking, do we maybe need deployment targets for DAC for 2030 and 2040? Because I hear a lot of talk also about learning rates and how fast DAC will eventually deploy. But I think most people in the room would also agree that DAC needs to get to a meaningful scale by 2050 to meaningfully contribute to climate change mitigation and not just to have a few functioning business models out there. So my question maybe to Dave, do we need deployment targets for DAC by 2030 and 2040?
So we absolutely do. And let me be the engineer for a minute here. If we're going to get this technology scaled, get it implemented the way we need to, there are certain things that have to happen, right? We need to see these technologies placed in the field and operated in multiple climates, right? We need to convince ourselves that if there are ice crystals in the air because it's snowing on the Great Plains that particular day, that's going to impact this technology this way. If there's a dust storm because you've got a dry month in Texas, then it's going to impact the technology this way. We need to understand how that's going to move forward, how the systems can operate, what their life cycles look like, how long the materials and the processes last under all those real world conditions.
It has to feel like I can have a career in this field because it's going to do something valuable for the world, and it's not perpetuating, inequalities or other harms. I think it has to feel like something where you can really make a difference.
Rory, Dave, is there anything government can do?
Yeah, I mean, so we've done an entire variety of things. So I have hosted Columbia grad students at Department of Energy to talk about opportunities to work, particularly in carbon dioxide removal and management more broadly. I also think one of the best things that our legislative branch has done is have qualified apprenticeship opportunities as a requirement for tax credits. So if you're claiming 45Q at $180 per ton sequestered into a saline aquifer for direct air capture, there are apprenticeship requirements the Department of Labor will set for that. And so I think as much as we need really smart integrated assessment modelers to tell us how much CDR we need, we also need people that have an understanding of how to build these operations at scale. And I think having a tax credit infrastructure in the United States, at least, that helps to build some of that workforce opportunity is going to be instrumental over the next couple decades.
Dave, you've got the last word.
And so sort of on the scaling and testing and, moving things up that TRL side, we have and will continue to make our facilities available and our expertise available to work with the folks that are out there who are just entering this field and trying to commercialize their great ideas. So we who've been in the field a long time probably have less brilliant and interesting and unique ideas than the folks that are just getting in, but we have a lot of understanding of what didn't work on other technologies in the past, and that can be valuable when combined with some of those sorts of things. So we're doing our best to make that experience available.
I see on our clock that it's time to wrap up the panel. I'd like to thank you all for your inputs, and to the audience, please give it up once more for our great panelists.